yeah, I think just before this, thanks a lot. I mean, so this is not going to be a physics talk. Okay. But hopefully it will be of, I mean, you'll probably be able to tell us about where one can take some of these things. Okay. So, yeah, so there's, just before the talk, I was saying that there's a canonical way of putting the words in the title together. And so what we'll start off with is by explaining the individual expressions. So there's percolation is one expression, hyperbolic groups is another expression, and we'll say what it means. Okay, so what's percolation? So here's the setup. You have a graph, any graph to start off with. You have a vertex set, you have an edge set. And you have a probability distribution on positive numbers, positive real numbers, which you think of as, I mean, positive real numbers you think of as the length of an edge, okay? So the probability measure space that you're looking at is an assignment of weights or lengths. This can be pushed here, right? Okay. Oh, should I put this in? Yeah. So there's an assignment of weights which basically says that every point in capital omega P gives you a geometric object, namely your graph. The underlying graph remains the same, but the lengths are changing, okay? So basically, if it's a single edge, it's, yeah, so you have a single edge, and so for here there is some, what's it, yeah, so row of E1, row of E2, so I mean, so these two could take different values in R plus, and you're going to get different versions of this graph, yeah?
So any length, right?
Yeah, you can, I mean, so the geometric information is going to be captured by the probability distribution that you have on R plus, okay? So the lengths give you, yeah, so for each assignment of weights, you have a metric on a graph, okay? So it's a, yeah. So what you have really is a collection of geometric objects, yeah, where lengths vary, and the parameterization space is a probability space, okay?
But do they satisfy triangle inequality?
So, yeah, I mean, triangle inequality will always be satisfied because, see, take a graph, take any assignment of weights, since they are positive. So there's some lengths that are assigned to various edges. You define the distance between 2 points as the sum of weights. I mean, the weight of a path is just the sum of weights. Now you look at the minimum sum of weights for all paths connecting two vertices. Yeah, that's going to satisfy the triangle inequality. Okay, so it's, yeah, so it's a collection of metric spaces. Yeah, all parameterized by some gadget, the probability measure space.
So you define a graph, and there are points on the graph, and you define distance.
You define distances.
On the graph.
Yeah, yeah.
Wait, distance on the graph means that the distance between 2 points,
Yeah.
of course, will be depending on how you go there. Right?
But you minimize.
Yeah, so you take the minimum over all such paths.
You take the minimum.
Yeah, take the minimum over all such paths, and that's.
Is everything finite or infinite?
Oh, all the graphs that we'll be interested in will be infinite. For finite fellows are not interesting in this context.
How do you know the minimum makes sense?
No, they do. No. That's it's actually easy. I mean, the point is that there are finitely many paths, so it's bounded from below.
Okay.
That's it. Okay.
Many paths, why the finite?
Hang on. Yeah. So that's so you take the infimum. You take the infimum. No, that's also not going to be. No. It's going to be. It's good. It's just a compact thing, so you'll be able to extract an infimum. Yeah. Okay. You won't be able to see. The point is, yeah. Here's the thing. You won't be able to decrease. You won't be able to decrease beyond a point. Yeah.
I understand.
Finally, it will be a probability zero event. If it does not exist, so you throw it away. Yeah. That's it. I mean, and everything that we'll be doing will be up to finite fudge factors, small fudge factors. So even if you have an infimum, if you take something that's sufficiently close to it, it will do the job. Okay, so now, so now let's formalize this. So essentially, what you think of this is that so each edge gives rise to now a function, yeah, which assigns the length. So that's your function, which gives you the. So this is some random variable. So each edge gives rise.
Percolation, the edge is on or off. Here you're allowing
So hang on, yeah. So,
allowing something more general.
yeah. So the thing is, that's not, I mean, there are various flavors of percolation. This is, so this is what we are doing is called first passage percolation. What you are saying is that that's sort of Bernoulli percolation, yeah? So that's why I have allowed infinity to be in, so that you can put,
Off will be infinity.
off will be infinity. To travel across an edge will take infinite amount of time.
Yeah.
So yeah, I mean, from a mathematical perspective, Bernoulli percolation is sort of, what do you have? So again, going back to this,
You have infinity or zero.
let's see. So let's draw some picture. So yeah, so you have, say, so you have your measure space omega p, and you have some little omega. There's a point here, and above this you have your graph. Yeah, and the underlying graph is essentially the same. Yeah, over all points. So you have some omega 1. You again have this same guy. Yeah, this will be some infinite guy. But and then, so what's happening is that only these lengths are changing. Yeah. So if you assign infinity, it means it takes infinite time to percolate along it. In other words, it doesn't percolate along that edge. That's all. Yeah. So it's just to put all these two things, these two favored models of percolation, first passage and Bernoulli, together in one framework. That's all. But I will not be doing Bernoulli, so stuff is that's going to be of interest in the talk is going to be open infinity.
Given a row, you'll define the distance between 2 points as rho of some.
No, rho is a probability distribution.
Right. So
Each edge has a number associated.
So rho is going to, so rho is a probability distribution. It comes, so rho is a measure on R plus union infinity. Okay, so that's stuff that models the base. Yeah? I mean, it's essentially you'll take a collection of these geometric objects and you'll ask how much of the total number of geometric objects that is. Yeah, so that's going to be some subset here. Yeah? You're going to ask for the probability of, I mean, for the measure of that subset. How
Independent on each link?
yeah. So now, okay. So now the thing is that this random variable xe, which assigns weights. Yeah. So weights are assigned. So lengths are assigned without any. I mean, so this is a specification. This a priori, this omega p could be any measure space, but now we make it more specific. The weights assigned to different edges, lengths assigned, are done completely independently and with the same distribution rho.
So identical.
i.i.d. Yeah. It's yeah. Independent, identically distributed. Okay. So that's the meaning of this. There's some probabilistic terminology, i.i.d. with log.
Small omega notation.
Omega is a point here, this guy here. So it's a, yeah, so basically this is again, I mean, if you have a probability space which is capital omega, then a point in it is little omega.
So I would think of it as a random lattice, and each of its omegas is a realization of that random lattice. It's quenched disorder.
Yeah.
That's physics language.
Yeah, no, this is also the probabilistic language. I'm a geometer, I'm not a probabilist. So I think of this as a space and points of it parameterize the geometric objects. Okay. But yeah, I mean, it's exactly, I mean, that's a linguistic difference. It's, yeah, okay. So now, let's see, so you have an edge path. Gamma is an edge path. So for omega belonging to the sample space, the length of that path is just the sum of weights, okay? And the distance is the infimum. I've been careful, see? Okay, so that's your distance. So this now, so the distance between 2 points is now a random object, which means it's parameterized. So if you input 2 points, so now the underlying topological space is fixed. So you have 2 points x and y. For each little omega, you're going to get a distance. Yeah? So the distance is going to change over the space. So what you would really, I mean, the kind of questions that you would like is expected behavior of this distance. Yeah? Rather than, I mean, so if the space was a single point equipped with the Dirac measure, you would have a deterministic setup, and then you would be doing what we call geometric group theory. Okay, so that will be the next slide, but come to that.
Rho here is fixed.
Rho here is going to be fixed. We are going to impose restrictions on rho which furnish reasonable conclusions. Okay. All right. So this is one of the geometric objects that we'll be studying is the distance. The other geometric object we'll be studying is the geodesic. So what is the, so for each sample space, there is some geodesic between x and y. Yeah? So the shortest, the realization, and that's called the FPP geodesic. And this realization does go through under reasonable assumptions on rho.
But there may be more than one.
There certainly could be more than one, but that's a probability zero event. Okay? Because you're assigning things at random. Yeah.
Sorry, what's the
First passage percolation. So that's, so you can call it an omega geodesic or a percolation geodesic or a first passage percolation.
How is this different from d omega?
D omega is a distance, this is a path. This is a geometric object whose length is d omega. Yeah.
So if I understand it right, given a omega, that gives you a probability distribution for choosing given a rho, that gives you a probability distribution for choosing little omega.
Exactly.
And once you have given a particular omega with some probability distribution, you can calculate the distance between any two points and calculate.
Yeah,
the
so
minimum.
for the probability distribution comes just for measuring little omega. For each omega you have a geometric object.
And then
yeah.
you calculate the
Yeah.
smallest distance.
Yeah. Okay, and so again, so basically putting packaging.
You'll be interested in the distance between any 2 points.
Absolutely. So this is, so basically now you get a random variable, txy, each point of your probability space spits out the distance. Okay. So this is called the first passage time between x and y. Okay.
So rho is i.i.d.
Rho is
The
i.i.d.
graph need not be homogeneous in the sense.
The graph could be anything.
Need not have translation, need not have anything.
So far, but the situation I'll be interested in, it will have.
Will have.
Yeah. So that's the next slide. So we'll come to it. Yeah. So this has been, okay, so this is first passage percolation, and it's widely studied for Zn. Why? Because it's Hammersley and something Broadbent or somebody. So basically you just put some water on the floor, classically studied for Z2, model the plane by the grid, discrete Z2 lattice sitting there, and essentially you have rho i.i.ds on each of the edges, and the water flows, you basically ask how fast it will reach one point, how fast it will reach another point. Okay?
I didn't understand. What was that? What is it?
Pardon me?
I didn't understand what
The
you meant.
lattice.
Oh, Z2 is this. So this is your graph.
Square lattice.
Yeah, square lattice. And then, okay, so this is 0, 0. And this is, so this graph, this gamma, is now this.
It goes on forever?
Yeah, it goes on forever.
This is called Z, I see. Why is it called Z2?
Oh, because it's the,
Valued points.
Oh.
yeah.
Oh, that's Z2. Yes, thank you.
Okay, Z cross Z. Okay, fine. Is there something else that's called Z2? I don't know.
Z2 is reflect. Sort of
Oh, Z mod 2. Oh, okay. That is Z, this. Yeah. Okay, yes. Okay, fine. Or Z2, whatever, Z sub 2. Yeah.
So is there a notion like a percolation transition where if x and y are infinitely separated, then you would have paths between them?
Infinitely separated means?
Meaning that if you have a slab, so for finite
Crossing
this is what would have been the
He's asking
thing that
Ah.
you have a point on top and you have points.
Can you go from top to bottom?
Can you go from top to bottom? Since you have an infinite slab, so I don't know how to even ask that question.
No, you can ask.
So no. So suppose this is your graph. So what you have here, every point will be connected to every other
So
point.
he's simply saying if you start at one end, take a point somewhere.
Yeah.
And on one slice.
Yeah.
And take a point on the
Ah,
slice.
but okay, for
Crossing probability.
I understand. But then for infinite guys, there will always be crossing. See, the thing is, it's
He never had blocks.
yeah. So you're thinking of a finite piece.
Yeah, slab.
From here to here, will it push off here or will it go all the way across?
Right.
No, he's
Yeah.
saying is there a path connecting from left to right?
But he never has blocks, so there's always a path.
Yeah,
That's what I'm saying.
there's always a
If
path.
that was only infinity
No,
or zero,
suppose
Yeah.
that
That will be the
I
path.
So that's
I
Bernoulli
keep
path.
the points x and y,
Yeah.
make
Far.
them
He's never cutting.
farther and farther away,
Yeah.
and there is still
They will all.
He's never cutting the limit.
Yeah.
If his probability distribution was either some probability zero, some other probability infinity,
Yeah.
then that would be what you're
So Bernoulli, for the Bernoulli model, this is a reasonable question.
to ask
Yeah.
on that.
But for this, I mean, there will be small probabilities if your thing becomes.
But you could ask instead, how is the time scale?
Scaling.
Yeah, that's something I'll come to.
Yeah.
Okay, that's something I'll come to, but in a different geometry. Okay,
Right, not in this.
not in this geometry. Okay, so here actually, I mean, as you can see, from 0, 0, typically I mean, this is a problem that was probably formulated in the 50s or something like that. Anyway, if you look at the number of paths from 0, 0 to nn, yeah, that's pretty large, 2n choose n. But if you have, so essentially take the 2n comma 0 guy, that's just one guy, right? So the number of paths increases till this and then this decreases again. And if you have the number of paths from 0, 0 to nn increasing fast, I mean the number of geodesics increasing fast, yeah, the chances of water going from here to here is much larger than water going from here to here. Oh, take the number of geodesics. What are the geodesics? They're just the deterministic geodesics. Yeah, the word so geodesics means the shortest paths.
Depends on your assignment of omega.
Yeah, so I'm saying deterministic. So assign 1 to everything for the time being. So it will be 2n choose n. This will be 2n choose 2n, and so on. So the thing is, there's a chance that so it will be. I mean, it will be all uniform, identically distributed. So water has a much larger chance of percolating from 0, 0 to nn than straight across. Okay? So which means that, so this is sort of the idea would be that the velocity, or speed of percolation to these points would be larger and would not be uniformly distributed. Okay?
Percolation only cares about the geodesic, not the paths around that geodesic.
Yeah, so you're going to take this random variable, you're going to take an expectation, right? You're going to take an expectation of this time, passage time. So we'll call it speed or velocity, but we are really referring to is 1 by velocity. So passage time by distance. Yeah. So this will be shorter for these guys and larger for these.
No, I mean, but the still the quantity that you would be looking at is, let's say, d omega, right?
Yeah.
But if you find d omega and why doesn't, I mean, okay, that maybe is your model, but in principle one could also care about the paths that have slightly larger distance, right?
Yeah,
So
but
if there is a particular pair of points with d omega.
no. So there are two things. D omega will be realized almost surely uniquely.
Yeah.
That's the distance, in omega. Yeah. Now, so which means what? So now you're going to take the expectation of that. What is the expected distance divided by the deterministic distance, right?
No, I'm saying even for fixed omega.
Yeah.
You could choose to look at paths not just which are minimum distance, but also in the neighborhood of that also, right?
Sure. What would you want to do with that?
I mean, the percolation physically should care about that also.
No, percolation. Okay, so the thing is, each assignment allows you to travel. So water at each point. The model is that the water is flowing where it meets least resistance, right? So there is a chance of it going different way. I mean, it's not that it's the whole body of water is going. So it's
the probability distribution of d omega.
Absolutely. So that's exactly what this is doing. So d omega is now a random. I mean, t is now a random variable. Okay. So it is actually encompassing all that, but the nearby paths. It's not for a fixed omega. I mean, the nearby path is being taken really by a different probability distribution.
I thought you were asking Abhijit, why is the fact that there are many geodesics, why does that say that this is faster this way than straight?
No, that was only for this case, I think.
Just for this one.
But even for this case, why does it say that?
Oh, because it has many more ways of reaching that.
But they are asking why you need to consider the different ways you can do it. You take any one way, it can travel a certain.
No, but so basically
multiplying by the number of possible ways.
Yeah, so you're going to average this out, right?
It's taking the expectation value.
Yeah, you're going to take the expectation value. If it deviates away from this, it is going to become larger.
No, wait. There's two different things I can do with d.
Yeah.
For d, there's a unique thing.
D,
It's the minimum.
for each omega, d is a minimum.
Yeah, so then you are just looking at the extreme value statistics of the path length.
Yes.
Right? Which is different from averaging over all the geodesic, in this case there are many that give you the same one.
Yeah.
In your case it will be only one.
No. So the thing is, this is the deterministic paths are many,
That's
right? Now you're going to give you, so on the take the average. Yeah. Average, so if you assign the average weight to everything, that means there are any path of this length.
Yes.
Yeah. The average is going to remain the
Average
same.
over all paths of a given length.
No, you're going to average over all all probability distributions, right?
In all probability distributions, in each realization of the probability,
Yes.
you pick one number.
Absolutely.
Which is the minimum T.
Absolutely.
An average
Average
over
over, that's
so
correct.
then how many paths there are doesn't enter.
Exactly.
It's like
No.
disordered
Unless you
noise
want it to
classical
be.
theory.
No. See, the thing is, if you're going to assign probability distributions at random,
You have
Yeah.
disordered
the expected
classical.
distance, the expected length of all of these paths is the same.
No. So in this very particular case, where there's this massive degeneracy
Exactly.
of
The
minimum
expected
path,
length of all these paths is the same.
But I'm saying you could just say that length value is the minimum length.
Is 2n, right?
Is whatever it is.
That's correct.
And I'm just saying in this case the probability distribution is just a delta function at 2n. I don't care how many paths realize 2n.
There's not even a probability distribution.
Yeah,
Length is 2n.
I know, but if he wants to
No.
take in the random case,
Yeah.
there is
You,
a minimum
if you put a Dirac,
but in
yeah,
your
sure.
random case, there is a value for the minimum. in
Yes,
the
yes,
realization.
yes.
And you look at its probability distribution. That probability distribution cares nothing about how many ways there were of realizing.
No, there'll be a clustering around that. So the thing is, what is the idea? So in one probability distribution, this guy is a minimum. In a nearby probability distribution, you'll have this guy as a minimum. You won't have that kind of a situation here because of the lack of degeneracy.
Yeah, I understand. But so what is the probability distribution you are defining? It is just take the value for every realization of the lattice. I have a minimum.
Yes,
I put it in a bin. Then
Yes.
next realization, I put it in a bin.
Yes.
Plot that histogram. That's what you're doing.
correct.
But if in a particular realization there are 11 ways of realizing the minimum,
In-
you put 11 in the bin or not?
No. So I throw all those 11 out because that's a probability zero event.
So I'm saying in that case, this issue doesn't arise. This issue of 2 and choose and kind of thing, there's no such.
No. The reason 2 and choose n arises is because
It's a highly degenerate case.
because it's highly degenerate, you perturb the thing slightly. You choose a probability distribution. I mean, for each assignment of weights, you choose a nearby assignment of weights, the path changes a little, right?
Correct.
Oh, very much.
Huh?
Given the
Changes
model,
very
there's no
much.
average. Once you pick the distribution.
Yeah.
I understand. So you just look at whatever that number is. You don't wait.
So
it
why
for
is the
some
degeneracy?
factor.
Why does the degeneracy matter? For what?
It doesn't.
For what question does it
It doesn't
matter?
matter.
It doesn't matter.
No, degeneracy does matter to
What
give you
question?
velocity, to compute velocity. You are
What
going
is
to,
the velocity?
we'll come to that, okay.
So there is different averaging you're doing where you put 11 in the bin. If there are
No. If you put 11 in the bin, that's going to be inside, in this probability measure space, that
It's never
11
gonna
is never
happen,
going to
right?
happen.
That's why we are wondering why you're bringing up the degeneracy.
The degeneracy is in the deterministic situation. So nearby probability assignments is going to choose one of these paths with high probability.
Yeah, that's true.
That's the thing. So therefore you are going to get things which have more or less deterministically the same length.
Yeah, you've got a very
Sure.
peaked kind of.
Sure.
Yeah.
Sure.
Which will not happen when you have 2n comma 0, where you
So
don't
you're
have
now trying
degeneracy.
to ask which variable should I look at? Should I look at x comma y where y is diagonally separated from x?
No, I am going to not even look at z2.
I know, but in the analogous case.
Yeah, in the analogous case, this is the motivating example. I'm just trying to sort of say that the point is that the velocity in different directions will be different.
Yeah, so but let me ask a very concrete question. In Z2,
Yeah.
if you did this problem,
Yeah.
probability
Yeah.
distribution.
Then there is
The probability distribution of D of x comma y.
yes,
Will it depend on the vector x minus y?
of course,
or
not
in the
x comma y. It will
Of
depend.
course, that's what he's saying. I think. He's saying
No,
the
it cannot, in the Z2 case, it cannot depend on x and y. It has to just depend
X
on y
minus
minus x.
but it depends on the direction.
As a vector.
Yeah.
Between x and y meaning here.
Yeah.
Yeah, it will depend on, okay, I was thinking of this guy as little x comma y.
Oh, yeah. So take the vector separation between
That's
the
right.
points.
That's right.
You're saying this probability distribution is quite different depending on the angle of that vector.
Exactly.
And I think he's saying
Exactly.
it's very peaked if it's 45 degrees
Yes,
and very broad if it's 90.
that's right.
The probability
Distribution for the length will be very peaked at
No,
45
not for
degrees.
D. For D is different from the length. D is the geodesic distance.
Yeah, that's what I mean. The probability distribution for D will be very peaked. Because there are so many geodesics
Yeah,
that this will peak it up once you've got a probability distribution.
yeah,
Whereas the other guy will become broad.
that's right. That's correct. That's correct. That's exactly right. Yeah,
So
that's
the
it.
probability distribution of D is going to be more sharp
Yeah,
when
yeah.
y minus
45.
x is on that 45 degree.
Yeah.
I think that's what it is.
Yeah. And hence, I mean, the thing that you want to extract is expected time of passage divided by the usual, the determinate distance 2n. Yeah. So expected time of passage from 0, 0 to nn divided by 2n, yeah, is going to be smaller, yeah, it's going to be smaller here and it's going to be larger here.
Yeah.
That's all that I'm saying.
Yes, yes.
Because there are many parts near the minimum.
Many parts near the minimum, that's it, that's all. So it's actually,
Yeah.
yeah.
So, just to this,
No, so that's not.
so there are 2 to the power 2n possibilities.
No.
The probability distribution is that there are 2 to the power 2n possible paths.
Yeah.
Each one of them has probability distribution 2 to the power minus 2n.
2 to the 2n from where?
From, if you
Oh, you take all parts of length n?
That's right. And I'm constructing a probability distribution.
Yeah.
So I must assign 2 to the power minus 2n to all of them. And there is only one path for this, the straight guy.
Yeah.
So it's just 1 times 2 to the power minus 2n.
That's provided you are assigning weights to paths by the uniform distribution on the space of paths.
So I'm saying that you have taken the Dirac delta function in which each guy is just 1. Then
Okay.
this is how the counting will go.
Yeah, but there's another issue. So basically, you want to, in that case, you will always want to go forward, right? A geodesic will not be realized by some path which comes and intersects itself. So you'll have to look at self-avoiding paths. So it's going to be a little, I mean, the count is going to change a little from that. So essentially it's going to be what? I mean, you can take one step to the right or one step. That's a different model. It's called last passage percolation. You can take a step to the right or up. If it's percolation just in this quadrant, yeah, then you can only, I mean, percolation paths cannot intersect themselves because percolation geodesics can never intersect themselves. Okay, all right. So this is,
Sorry, let me just say.
Yeah.
So the point that I was making was that if you have a path
Yeah.
for a particular omega, the geodesic,
Yeah.
right? You are integrating, so you are finding out the distance, you are integrating over the omega.
yes, that's going to be the expected
Right?
distance
The expected,
between,
not
yeah,
the expected distance. But I'm saying for a given omega,
yeah.
you would integrate over paths also
For
with some
each,
measure.
no, for each little omega.
For each little omega.
For each little omega, there is no integral. There is a sum and you take
are
the
not doing
infimum.
it, but
Yeah.
one could do that also, right? That one could integrate over the path space with some measure.
Yeah,
But that is
that's not what
that's
I'm doing.
different, yeah.
Yeah, that's a completely different problem. I'm certainly not
And the
attempting.
percolation of water doesn't care.
Pardon me? Percolation of no percolation. I mean, the point is you assume that bits of water trying to take the least path and in a probabilistic thing. Yeah.
This is quantum motion.
Okay. Okay. So this is one word in the title. So we'll go to the next one. What about hyperbolic groups? So I will not study percolation on. I mean, there are several classical problems left, and what we'll be doing is we'll be translating. I mean, we'll be changing the geometry underlying the space. Yeah. And we'll be doing percolation there. Okay, so what's the geometry here? Yeah, and the way to say this is that in some sense, if you take a finitely generated group at random, yeah, in some suitable sense, it's actually hyperbolic. It's got probability 0 of being Euclidean. Okay, so what's a hyperbolic group? So let's go back to the deterministic situation, and so if you have, let's see. Suppose this is a deterministic guy, so you have a Dirac mass supported at the point 1, yeah? Then what you're getting is a structure of a graph, and now we'll introduce extra symmetries in the space, yeah? So which means essentially that there's going to be a group which will act transitively on the graph. The graph can be actually abstractly extracted from a finitely generated group. So you have G is a group, S is some generating set, yeah, which is finite. The vertex set consists of all elements of the group, yeah, and the edge set consists of pairs of group elements G comma H, such that G inverse times H is actually in your generating set. Yeah. So what I had drawn, this Z plus Z lattice that we had drawn here, that's the group Z cross Z with generators 0, 1 and 1, 0. Yeah. That was the Cayley graph that we had drawn here. So Z with the standard set of, okay, let me just draw two. So Z with the standard generator plus minus 1. So I'll assume that the generating set is symmetric, which means that if some little g is in the generating set, g inverse is also in the generating set. This just makes your graph undirected instead of directed. Okay? Okay, so z with plus minus 1, this is your Cayley graph. Okay? This is 0, 1, 2, etc., etc.
So by construction, this graph will have some symmetry, like S will be roughly the symmetry of the graph by
No. S is just the S will be the generators of your symmetry.
So given a group G,
Yes.
S is some subgroup of G.
No. S is a finite set.
Just a bunch of things
Product
that
of
generate
these
everything. You can
Yeah.
get the whole thing by multiplying as much as you
Yeah.
like.
So I mean, for example, you think if you want to have a continuous version of thing, think of the Lie algebra and finitely many guys which span the Lie algebra.
So some subset of the generators.
No, the whole generators, all the generators.
You need them all. No?
Yeah. Otherwise, you won't get that. It will be a disconnected object. So I mean, think of z plus z. You take 0, 0 and 1, 0, and then their inverses.
Yes, sir, discrete group with
Yeah.
like a finite set of generators.
G itself is the same.
Yeah. G is the symmetries, obvious symmetries are exactly G. And I'm not going to be interested in other symmetries. Okay.
Only two vertices in the graph are connected by an edge if they
Yes.
differ
By a generator.
Action of one generator.
Yeah.
like you're saying.
So a generator takes the initial vertex to the final vertex, then you connect them by an edge.
So the neighbor function is the set defined.
Exactly. Exactly. So a priori this depends on the generating set that you choose. Yeah. But all our conclusions will be independent of it. Okay. There will be some qualitative. I mean, the qualitative features will not be dependent on that.
But is the generating set minimum?
No, you don't care.
You don't care.
You don't care.
So then you can make it larger and larger.
Of
and
course you
larger,
can.
And it still won't matter.
Qualitative behavior will not matter. The constants will become worse and worse.
Sorry, in this.
So I'll draw. Let me just draw one more picture, and then you'll see it. So this is 0, 0. This is the generating set plus minus 1. Okay, for z. So this is g equal to z. S is equal to plus minus 1. Okay. G equal to z. S equal to plus minus 1 plus minus 2. Okay. Yeah. So you get. Okay, let me just draw the picture. So this is 0.
Oh, like, okay, because one of the just takes you diagonally and then the other one takes you. Very nice.
Okay. So if you looked at it from far and you had bad eyesight, you'd see that these two things are the same.
That's
Right?
what you're saying.
Okay.
So if it was so this is a, so what about?
This is a way to sell the field. I mean, if geometry can be done with bad eyesight.
Tough question.
Finite generating set, right?
Tough
Yeah.
question. If
Yeah,
it's Z mod 2, that's your group. Then what Shiraz calls Z. Then what you get?
You take all finite groups and you throw them in the dustbin. They're all points.
Just get a point.
Yeah, you get a complete graph. You take all the elements in the group, you're going to get a complete graph on however many. This is not interesting. Everything is connected to everything else. It's a complete graph. Huh? Yeah. So it's not. I mean, it's basically qualitatively, it's a point. In this sense.
Qualitatively, it's a point. Okay,
Yeah.
some object.
Is it a complete graph?
Yeah. So
It's a complete small graph.
yeah. So there's a way of formalizing the way of going between these two. So if you have a group G, okay, yeah. So
Why complete? Because Zn, if I take Zn. and
what is
Z
Zn?
mod
Z to the n or Z sub n?
Z mod and Z.
Yeah.
And then if I take the generator to be just one cube.
Yeah.
You're going to get a cycle.
It's not
You put two
complete.
fellows. No, you put. That's true. I'm saying that you take all the elements. If you take all the elements of your group except the identity to be the generator, you're going to get a.
It's not always will you get a complete.
Of course not. Of course not. No. It's actually where I mean I'm lying slightly when I say that you
But
should
you
not.
don't care. All polygons, all things with diagonals, everything
Yeah.
is a
For
point.
the problem that I am interested
They're all
in,
points.
they are all points.
Okay.
Okay.
Good.
And the answers you said don't depend on S, but are they not supposed to? A priori?
The qualitative features. Yeah. So there will be. Okay. So what
In some
happens?
sense, all things to do with Z are 1D.
Yeah.
Whether the graph has some property or not doesn't depend on S.
Yeah.
But to what extent it has a property will depend.
Yeah. So I am not going to be interested in exact constants.
Yeah.
Yeah. What is the exact velocity will change. Yeah. But whether the velocity is greater than 0 or not will not. Okay?
So for just to fix this, if it's z cross z and I do plus minus 1, plus minus 2 on in both directions.
Yeah, you're going
then
to
I
take.
get a square lattice with crossings.
Yeah, of course.
Yeah.
Yeah.
Got it.
You're going to get this along each direction.
Correct.
Yeah.
Square lattice.
Yeah, I mean basically it's going to be the product of this guy with the other guy. Just take the set product. Yeah, there will be squares. You knock out the squares. That's it. Yeah, for each edge cross an edge is a square, right?
Yes.
So you're going to get just you remove the interior of the thing and you're going to have a grid for that. So it's going to be this guy, this graph, cross itself, and take the one skeleton. Okay, I mean basically knock out the flesh.
Plus minus 1 in each direction, I would have got the square lattice.
Exactly.
Right?
Exactly.
So plus minus, then I get those crosses.
You're going to just take this guy along with, I mean this will be in the one direction, the same guy will be in the other direction.
Not just crosses.
You will get more than that.
Product of this.
It's just a product of this guy. And
Okay.
so for each edge here, you're going to have the same guy. For each vertex here, you're going to have the same guy.
Direction.
Yeah.
It's not planar.
Yeah, it's not going to be planar. It's not going to be planar.
It's not a planar.
No, it's not a planar. I mean, take a triangle cross a triangle, so, and knock out the two cells that you get.
Yeah.
What do you get? You get some
Yeah.
slightly involved object. Yeah, it's not planar.
So the other two-dimensional lattices we're used to, like triangular and so on, don't come out of something.
That can be finished. So, for example, I mean, if you have, so for example, I think if you take two of them in one direction, one in the other direction, maybe something, maybe. I'm not sure. Okay. Okay, but anyway, so this is how it changes. What is the correct map? I mean, what is it that says there's a class of maps which essentially say that if you declare that two fellows are the same, if they are interchangeable by this class of maps, there's going to be some equivalence. So what happens is that this guy has a distance, this graph has a distance just by counting the least number of edges, and we don't have the infimization problem at all because it's actually genuinely finite now, and that gives you a distance on this path. Okay, so and it's also a geodesic space. So what's a geodesic metric space? Where is it? Yeah. So a geodesic metric space is, okay, so what is a geodesic metric space? Any 2 points can be joined by a shortest path. Here, you are allowing degeneracy and all that stuff, okay? Because you're in the deterministic setup, you don't have the luxury of having a continuum many values or probabilities, okay?
The distance is just number of links.
Yeah, but you think of it as, so from here to here, this is a geodesic, this is a geodesic. There are two geodesics there, that's it. Okay, all right. So now so this is what Cayley graphs are. But so gamma is equal to, let's say gamma 1 is equal to G with symmetric generating set S1. Gamma 2 is the same group, symmetric generating set S2.
But this is the same as the previous notion with all lengths being 1.
That's right, exactly. So you start off where Dirac is, it's a probability distribution is Dirac. Yeah. So now the thing is, if you have gamma 1, gamma 2, if it's the same group, so the collection of maps is, so f from say xd1, let's say xd to yd prime. These are geodesic metric spaces. Okay, so any 2 points have a shortest path. This is called a k epsilon quasi isometry if.
Sorry, what is XD and YD?
Oh, these are just two geodesic metrics. Think as graphs. Think graphs. Okay, arbitrary graphs.
This is a map from one graph to another?
Yeah.
F.
Just a map. So
Okay.
yeah. Or it's just think of these as metric spaces, nothing else.
Okay.
Yeah, the edges will complicate the thing. You don't need them. Just think of these as collection of points with distances between them.
Fine.
Okay. This is a k epsilon quasi isometry if A 1 by k d prime fx fy minus epsilon less than equal to dxy less than equal to k. Let's do it the other way. Yeah. dxy minus epsilon less than equal to dfx fy less than equal to k dxy plus epsilon. So if this epsilon was 0, you would just have a bi-Lipschitz map. You're stretching everything or contracting everything by some bounded factor. Okay?
Prime is for points in y.
D is for.
Distance in y.
Okay.
So the distance in y.
Yeah.
So
K is a fixed number.
k is some fixed number. So this is, it depends on this k and epsilon. So k is a fixed number means that all lengths are stretched or contracted by some bounded amount.
Some small error.
But there's an additive error which allows you discontinuities. Okay. So this epsilon is basically you can tear your space, but so long as after you tear the 2 points that you get by tearing, they don't go too far. So the same point does not know where to go, but the amount of ambiguity in not knowing where to go is bounded. Okay? So for example, if you just have, okay, again let me draw this grid. So you have this z plus z sitting inside R2, yeah? Z plus z, its inclusion in R2 with the usual Euclidean metric, that's a quasi, okay, so the second condition is that for all, yeah, so y is contained in a, let's say k neighborhood, just to absorb the constant. Actually you should probably put k epsilon c, but I don't want to do that, fx. So basically the image of x, so because it's bi-Lipschitz, it's more or less an injective map. Yeah, only points which are nearby could collapse. Yeah. The thing is, it's more or less fills the space. If you allow yourself a k neighborhood of the image, you get the whole space. Okay, so not clear. So basically, it's, yeah, you've taken x and you've embedded it in D. Yeah, this is so. For example, just take z. Yeah. With the usual metric. Now it embedded it in R2 isometrically, yeah, by the isometric embedding of R. That's going to be a QI embedding. It's going to satisfy only this condition. Yeah? But all of R2 certainly does not lie in a bounded neighborhood of R. Right? So the second condition says that all of the target space actually lies in a bounded neighborhood of where you've gotten to by pushing in the first space. Okay? For example, just look at the collection of lattice points of Z2 sitting in with this word metric, sitting in all of R2. Okay? That embedding of Z2 in R2 is a QI embedding because every point you take a one neighborhood of it or two neighborhood of it, you're going to get all of R2. Yeah, that's all. Yeah. So the reason why I don't care about constants is that 2 could be a million. It could be 10 power 90, whatever. But I don't care. Okay?
Bounded neighborhood is just anything.
Yeah, but the only thing is that the bound is fixed for the universe of discourse. For the problem at hand. Yeah.
This is roughly defines dimension.
No.
Because R3 is no way this.
Okay. So I get your question. So for Euclidean space.
Yes.
So what is the precise way of saying that is that the dimension of the space is a QI invariant.
Okay. Yes.
Okay?
Yes.
So that's correct. That's correct, but it requires a proof. Yeah. And it's sort of it's something that you would expect, but it's not entirely trivial to prove it. Okay? You basically have to get some coarse topological property of, because these are now not continuous maps. R is not homeomorphic to R2. You can't get it by twisting and turning and stretching. Was something that end of 19th century was an open problem. Yeah. And in fact, Cantor thought he had actually proved that it's not true. Yeah. But then Brouwer actually had to come along and prove that. So you need a coarse version of that Brouwer's theorem to get this through. So much of it is, this is essentially topology with control. Yeah. Okay. But distances can't be stretched arbitrarily. That's the only thing. Okay. All right, so this is one example, but the other thing is that from this, if you have a quasi-isometry from one space to the other, what this definition gives you is there's an inverse map, which is also a quasi-isometry. What is it in this case? You just take these, say, take a one neighborhood, yeah? Take the dual tiling, for example, yeah? Take each tile and collapse it to the lattice point there, yeah? Now this point here does not know whether to go here, 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 but the points where it could go to that have a bounded amount of ambiguity.
More generally Voronoi cells.
More generally Voronoi cells, any kind, yeah, okay.
Even points on the edges.
Yeah, sure. But I mean, so the point is that that confusion in those points is bounded amount. Okay, that's all.
It just goes to the nearest lattice point.
Yeah, choose a nearest lattice point and send it there.
Send it there.
If there is a more than one choice, then the distance is going to be some fixed
That's
time.
this epsilon.
That is this epsilon.
So there is one of these epsilons that's not going to zero.
Now, so here typically it's no epsilon will not go to 0. In fact, epsilon could be very large. Yeah. It depends on the diameter of your fundamental domain. Okay? No, okay, so fine. Anyway, so the thing is, that's what. So for us, the point is we'll be really, we replace 0 by infinity.
Yeah.
And therefore, I mean, we'll really be interested in asymptotics. Okay? Things going to 0 make no sense. You can't do calculus on these discrete spaces. I mean, the edges are here really a thinking prop. You can knock out the edges, and geodesics can be defined as maps of intervals in Z instead of R. Yeah, it's just a collection of points. So obviously, it's just a discrete space. It's just a collection of points separated by some definite amount. Yeah. So calculus goes out the window. Yeah. But you can still capture asymptotic properties of the geometry, and that's what we'll be looking at. Okay, fine. So now let's come to where. Okay, so why did I say all this? If you take a group and you have two generating sets, gamma 1 and gamma 2, it's not hard to see that each generator in the new generating set can be written in the first generating set by finitely many guys. So they are quasi-isometric. Okay. So if you want to study finitely generated groups, and therefore, and it goes the other way also. So finitely generated groups, the right collection of maps to look at, under which things are invariant, is our quasi-isometries. Okay. So this is the class is that is graphs with edge length 1. And the class of maps are quasi-isometries. So any reasonable theory that you try to build here should be invariant under quasi-isometry. Okay? And therefore groups, now you can really look at groups and forget the generating set. What Shiraz was asking, what if you make the generating set bigger and bigger so long as it is finite? Well, you want to look at quantities which are, or features, large scale features which are quasi-isometry invariant. So specific numbers will not be important, but non-vanishing or vanishing will be. Okay. All right. So now, what are the kinds of groups? What are the kinds of geodesic spaces, geometric spaces? Wow. What? Almost killed an hour.
Their seminars never end in one day.
Ooh. Okay. Oh boy. This is supposed.
K here is large.
Yeah. I was hoping to come to some statement. Okay, fine. Wait. So anyway, I won't give any proofs then. Okay.
So 115
So-
was really fine.
Huh?
If you got to 115, that's really fine.
I should try to finish by 1. Okay, but all right. So now let's come to the second word or expression in my title, hyperbolic. Okay. So what is hyperbolic? So geodesic metric space is hyperbolic if all triangles are thin, which means triangles look like this. What is the simplest example? Tree. Yeah. The A, B, C. What's happening is that AB, geodesic, is contained in AC union BC, right? So which means that each side is contained in the 0 neighborhood of the union of the other two sides. You allow yourself a finite amount of fudge factor. Yeah? That fudge factor is delta. Yeah? Again, this fudge factor could be arbitrarily bad. Yeah? But it should be fixed for. Yeah? Yeah? So basically, the thin means that the fat part here is bounded, uniformly bounded. It's equivalent to that. That's another way of saying it. Of course, Euclidean space is not hyperbolic because you give me some delta equal to 10 million. I'll say, okay, fine, you take a equilateral triangle of side 100 million, and then no side is contained in a 10 million neighborhood of the union of the other two sides. Okay? All right. So the archetypal examples are trees. Yeah?
Side here means minimum length path.
That's right. So once you have a geodesic, you'll have so the side is a geodesic. And once you have geodesics, you have triangles, etc. Okay.
Sorry, but this is a property of the underlying graph, or
It's a property of a space, of any geodesic metric space. We have not yet. It's of the graph.
So on there's constraints on the measures.
There is nothing to do with measures here. This is everything is the deterministic setup. Rho is a Dirac mass. for here. Yeah.
But
Then you will put some.
I see.
Yeah.
Okay, that's how
The probability will gel in a different way. So don't try to, right now, don't try to conflate these two. Okay, so these two are completely different components. One is percolation, traditionally done on Z2 and more generally Zn, yeah, or Zd, yeah. Hyperbolic groups done by geometers, yeah. We have no idea about probability so far. Okay, so then in the next slide we'll put these two pieces together.
By choosing a generator randomly.
No, generators, no, we'll come to that. No, generators will be fixed. Yeah, generators will be fixed.
So policity is
Okay. So here is the thing. G is defined, a group is now so this was just for a graph. A group is hyperbolic if the Cayley graph, which I drew, is hyperbolic with respect to some finite generating set, theorem. If it is hyperbolic with respect to some generating set, it is hyperbolic with respect to any generating set because of the fact that hyperbolicity is a quasi-isometry in that. Okay? Though the constants can become worse and worse. So this delta is just a prop. Okay, so such groups are ubiquitous. Okay, so here there is some randomness involved. Okay, so what is a model? I mean, okay, I've been working on this since my grad student days, so I should try to sell the field. Okay, so the thing is, if you take, say, some finite generating set, say no relations, that gives you what's the free group. Yeah? So the Cayley graph is a tree with 2 times the number of generators, what you guys probably call the Bethe lattice, right?
So, I'm sorry, but Cayley graph I missed. What is a Cayley graph?
Oh, this is the graph. The graph G is it's
The graph that you've been drawing.
Yeah. So for an arbitrary group,
generators.
The hopping.
the hopping graph is the Cayley graph because it was done by Cayley for finite groups. Okay. Okay. And there it was important what generating set he chose, but for us it's not.
If there are no relations, it's really a tree.
If there are no relations, it's a tree.
Automatically this triangle thing. That is this picture, right?
This is a local pair. Well, you'll have, you will take A inverse, B inverse. So it'll be in even valence, okay. Yeah, 2K because we'll be, okay. All right. Regular 2n adic tree. That's the Cayley graph of a free group. Okay. So what does this statement mean? Such groups are ubiquitous. You take all words, reduced words, which means you don't allow A and A inverse to be side by side. You don't allow B and B inverse to be side by side. Take all reduced words of length L. Yeah. So that's going to grow exponentially. It's going to grow something. Yeah. So let's say n sub L equal to cardinality of words of length L. Yeah. Okay. Now you choose relators at random from these. So basically, M sub L is some subset. Basically you're choosing some number of them. Yeah, out of all these guys. And declare that to be the identity. Declare those to be your relators. Kill those guys. Yeah. Now you look at this number log M sub L divided by log n sub L, and you look at the limit L tends to infinity. Okay. This guy, suppose it's D. So you choose a collection. Choose these guys at. So you fix a sequence just of numbers n sub L going off to infinity such that this limit exists. Yeah?
So finite fraction is generated.
So D belongs to 0, 1. Yeah, but it's in the log model that this guy is D is called a density. Okay. Now,
Sorry, I didn't get this part.
yeah.
Before that, you will expect your probability distribution when you will consider it to be a quasi-isometric.
No. Probability distribution, forget probability distribution. We are not talking about rho at all.
When we will consider,
we will consider. Now we are not. This has nothing to do with it. This is just about hyperbolic groups.
What a random group is.
I'm saying what a random group is. This has nothing to do with the rho in the first slide. So for the time being, just clean that probability. We have not put that probability and this setup together. I'm just trying to explain this line here. Why are such groups ubiquitous? What does it mean that if you pick a group at random, here that this random has nothing to do with the probability.
Yes. But if you want to do the beginning problem,
when not now, it will only confuse the issue. Right now it has nothing to do with it. Okay? We'll come back.
You are saying there are exponentially many words and you are going to have exponentially many generators in some particular
No, exponentially many relations.
Sorry, it's not, yeah.
Yeah, exponentially many relations.
Of that size.
Yeah, and now you assume that there's a limit of this. So basically, in the density, this is called the density model. Okay, so in the logarithmically, there is some number to which it converges.
Okay.
Is that guaranteed?
No, you choose. This is in your hands, right? You just choose a sequence of numbers such that this log by log converges to D.
And you're free to choose these relations as you want.
Yeah, so
There's no constraint that these relations have to obey.
they have to be distinct. Yeah, and you choose them at random, which means of all possible, there are zillions of, for each of these there is going to be n sub l, choose n sub l choices, right?
Correct.
You make all of them.
Ah.
No,
Yeah.
if you choose some relations at this layer, there would be those relations image at the next layer.
No, you're going to, the L plus 1 will be now for each L for L equal to 2. Yeah, for L equal to 4, there will be another collection of relations.
Yeah, but those L equal to 3 relations will translate into something at L equals 4 if you multiply them by A, let's say.
Yeah, could be. But that's true, that's true. But you don't regard, there is, I mean, you regard these as independent things.
These are independent.
Yeah, I
relations,
think
and that's how
that's
we-
independent less.
It's
Yeah.
really like
Okay.
what point you identify.
Yeah, because what you're going to do, so suppose this D is there. Okay, so here's the theorem, this is the theorem of Gromov. D greater than, if you put too many, G is trivial. You kill the whole group. Yeah?
Okay.
D is less than half, G is hyperbolic. So it's a phase transition. Okay? At D equal to half, you get anything. You get a mess.
Could you get like ZL for example?
So there are other phase transitions also that happen. D greater than 1/3, there's something called property T that kicks in. Finite groups have property T. D less than 1/12, there's another class of qualitative features that happen. And
Could I understand just an suppose your group was just Z.
yeah, what does it mean? Hey, I haven't said anything. What does it mean to say G is trivial? There is no G, right? For each density, what does this mean? It means that you look at the collection of groups that you get and look at the divided by the total number of groups possible under this condition. That number tends to this. It is, most of them are trivial. As L tends to infinity, it's going to be trivial with probability 1.
I see. Sorry, I'm going to ask a very stupid question.
Yeah.
Suppose my group is just Z, and the addition, the points on the line.
Yeah.
Okay. Now my relation, I just remove one lattice vector, 0 to 1. Am
Yeah.
I allowed to do that?
So here's the thing. I mean, this is true for number of generators. If you, yeah, there's for Z you don't get anything interesting. Number of generators greater than 1. So the free group you started off with,
Pairs of them.
yeah, yeah,
But my free group was
of rank 2 or more. Yeah.
It will become trivial immediately. At level 0 itself, it will become trivial. At level 1
Any
itself,
relation you put, you feel.
wait, Z is a free group
Z is a free group.
because I can keep multiplying.
Yes,
and get
yes,
everyone
but it's a
else.
very boring free group.
It's a very boring free group, but
Yeah.
anyway, for a moment. So now I just take away one of its elements. I declare
You
that to be a solution.
kill it.
I can, but yeah, so-
Not, you don't take away. You say declare that element to be trivial.
and then you have
And
to mod out
everything
the
is
group by that.
Mod out the group by that.
Then
Now I
everything is-
better understand. it.
Yeah.
Okay, now I understand.
Yeah, so those are the relation means you so basically if you kill n, you're going to get Zn.
Yeah.
I mean Z mod n.
The cosec by this.
Yeah. No, yeah, so it's actually you're going to take the normal subgroup generated by that in the group. Yeah.
You're gauging by that group.
Not quite. It's more than that. You're taking all its conjugates also and gauging by it.
If you take only generators A and A inverse, then
Yeah.
if you say A is 1, then everything is 1.
Yeah.
That's what it is.
So here it will be a power m is 1.
Yeah.
Then the next stage it will be a power n is 1. And typically you are going to get m and n relatively prime.
Yeah.
Then you are going to kill the whole group after just 2 stages.
But if I take Z2 and I declare 0, 1.
No, you don't start with Z2. You could do that. You could start with an abelian thing. It's not free.
Good point.
Free, it's not free.
It's free abelian, it's not free. You can do the same thing with any group you like. Yeah? And the theory is interesting when your group is rich. Yeah? Which means that all the abelian groups are very poor. All nilpotent groups are very poor.
So give us the simplest example where I can think of.
Free group. Take the free group on 2 generators. For that you think of that.
Free group with
Two generators.
If it's a free group,
Yeah, take the 4-adic
A
tree.
to the
4-adic tree. Now you take arbitrarily many words.
Four trees.
Those guys now become loops in your.
Correct. You start growing loops in your tree.
Exactly. So you pinch those points together,
Yeah.
right? And you do it equivariantly.
Correct.
Yeah. That's your new group that you get.
All those things.
Yeah. Exactly. Okay. So this is the reason that these groups are. I mean, these groups are interesting because you pick any group at random. It's either going to be trivial. The trivial group is hyperbolic for trivial reasons. Yeah. But I mean, otherwise, so essentially. Huh?
Okay, no.
I mean, all triangles are k thin, where k is 2, let's say. Yeah, okay. So, but all the other guys are. So here's the point. So now okay, so this is a problem which asks us to put these two things together.
The first line, if d greater than half is,
Yeah.
if d is greater than half, it's trivial because it's all the relations below that will kill roughly at that level, right? The whole thing at that level.
No, I mean, it's not, no, it's not like that. It's basically, if it's only it's an asymptotic statement. It's an asymptotic. The stuff that is below really does not have anything to do with stuff. It's just that there's going to be a lot of overlap. That's true. I mean, so that's probably the intuition, yeah. Okay. So now I'll come to your question about how do we put this stuff together with the probability distribution there. Okay. Here's the thing. So now what are our examples? Okay, so what are examples of hyperbolic groups? The Escher tilings are all hyperbolic guys. The symmetries, the space of symmetries of the Escher tilings that you must have seen. Yeah, this is sort of the skeleton. Yeah, so you actually, this is the triangle tessellation of the unit disk equipped with the hyperbolic metric. Okay, this is H2. Yeah, this is H2 with the Poincare metric ds square by 1 minus r square whole square. Yeah, or dx square plus dy square by y square upper half plane. Yeah, and this is a tessellation. The set of symmetries is a triangle group. Here it's 90 degrees, here it's I think what 45 degrees, here it's 180 by 360 by 12, whatever that is, 30.
So all Penrose tilings are obtained like
Penrose tilings are not periodic. No. These are periodic tilings. These are
periodic.
yeah, these are all periodic tilings. And the group action, the group is there. I mean, the reflection group in that triangle, it's a pi by 2, pi by whatever, 2 pi by 12. So pi by 6, pi by 4. And this is also a periodic tiling. It's a different, but this is I think 2 guys. It's a
What do
2.
you mean by periodic? I didn't understand.
Oh, meaning you take any of these tiles and you take a reflection. Yeah. So there's a group which acts on this tile, this space transitively, taking and that group is actually staring at you from the fundamental domain. It's a reflection here through 90 degrees. It's a reflection here through pi by. I mean, it's a.
Keep doing that. And
Yeah, you're going to get everything.
Translate.
Just reflect. Yeah, keep reflecting on all the sides, and you're going to cover this uniquely. You're not going to come back unless you. I mean, either you're going to come back to exactly itself, or you're going to go somewhere. Okay. When you come back to itself, that's a relation. So that's going around this.
It's going around a center.
So if you take, I think this one will be A, B, and C will be the reflections in the sides. A square is a relation, B square is a relation, C square is a relation because reflection squares is identity. AB squared will be around this valence 4 guy. Yeah? BC to the maybe what 6 or maybe 4 will be the other guy. CA to the 6 will be this guy. Yeah? And if you sum the angles, it will come out to be less than 180 degrees. Yeah? Therefore, it won't tile the Euclidean plane, it's going to tile the hyperbolic plane.
It's like a hyperbolic analog of Z2.
Exactly, it's a hyperbolic analog of Z2, but it was a square. If you cut the square into 2 right angle triangles, then you would get
It's the 2-dimensional hyperbolic.
it's a 2-dimensional hyperbolic guy. Yes, that's correct. That's correct. And there's something here also. Huh?
Higher dimensional also you can
Of
model.
course. In all dimensions you have existence. But well, I don't want to get into this. Okay, fine. Yeah, so yeah. Okay. So this is our friend, the free group on 2 generators. This is the Cayley graph of that. Yeah? One thing I just want to show you is that this boundary is a fractal here. It's a Cantor set. This is a fractal of dimension 1. Yeah? But that's really the right way to think of it, because you see what is happening is that if you do this tiling, then this part is becoming very, very crinkly. It's just converging by coincidence to something that's smooth.
And This is hyperbolic because the only way you get infinite distance is by going to the boundary.
Yeah.
And when you go to the boundary, all lines go sort of straight there, right?
Yeah, yeah, yeah. So for example, you can see those lines. For example, if you just, this is a diameter, this is a straight line. Yeah. And what would be, yeah, if you take one of these, there'll be these semicircles which hit the boundary at right angles.
So, so things can only differ significantly inside that you don't care about.
Exactly.
Yeah. See, you get infinite distances only by going to the boundary.
Yes.
So his hyperbolic notion was that the difference, this fattening,
Yes.
was some finite thing.
Yeah.
So that now you take two geodesics like this, one guy here, one guy here, one guy here. This is at the boundary.
Yeah.
Near the boundary, they do the same.
Yeah. So what is the triangle? What is the largest triangle that you can get in the oven? It's going to be this.
Yeah, like that.
So the biggest triangle that you can get, well,
Yeah.
the biggest triangle you can get is still bounded.
Yes.
Yeah? Therefore, it's hyperbolic.
Near the boundary, the parts are basically uniquely set by the boundary.
Yeah. So they are going to be tangential, and once they're tangential, the distance between them actually goes to 0 in the hyperbolic. Even in the Euclidean sense, it goes to 0, but the hyperbolic thing certainly
But
goes to
what was this about fractal 1 of dimension 1? That's the boundary.
The circle is a
Yeah, circle is a fractal of dimension 1. There's a boundary to all of these groups.
There is a boundary.
There's a natural boundary. Here it's a Cantor set. Here it's a circle.
Be adding something or the other.
Yeah, so don't think of that. That's a red herring.
Okay.
And I really think that paper is a red herring. What you have in mind, I think it's a red herring. This is the right context. The context is geometric. It has nothing to do with number theory.
It's a fractal of dimension 1.
Yeah.
That's generic or?
No.
No, right?
No. Okay, so here is the thing. For this d less than half, g is not only hyperbolic, but in a very precise sense, it is one-dimensional. It's morally one-dimensional. It's not a circle. I mean, it's actually a very connected thing. It's this Menger curve. It's typically a Menger curve. Okay. All right. So it's what there are various
Sorry,
characteristics.
tough question. When they say coastline of Norway is fractal, that's the same fractal as.
Yeah.
yeah.
And that dimension is not 1.
No. This is a topological dimension 1.
Oh, okay.
It's not not the Hausdorff dimension. The Hausdorff dimension is fractional. But for the circle, both are the same.
That's what I was asking.
Yeah.
In
For
that
the
case, especially, it turns out that it's the same.
Yeah. For the Cantor set, it's not going to be 1.
It's not. Okay.
Yeah. You could have anything between 0 and infinity. Okay. All right.
The topological dimension there, you are calling one the Cayley, the two variable Cayley graph.
For this, no. Here the boundary is Cantor set. It's a topologically it's a 0-dimensional object. Every connected set is a point.
log 2 by log 3.
Yeah. The Hausdorff dimension is log 2 by log. Yeah. For the regular Cantor set. Okay. So now we'll okay. So these are examples of hyperbolic groups. Finally, we can put the two pieces together. Okay. So now your underlying, so key feature of this hyperbolic group is the boundary. Okay. Now we want to go back to where we came from about percolation, but we want to run percolation on this, what I've tried to sales pitch it as the prototypical group. Yeah. Okay. And now what you want to do is first you get directions. What are directions? Yeah. So this is some discrete object. There's no continuous thing. You can't take derivatives. Right. I mean, the edges were some props, so you've thrown them away. There's no tangent direction anyway. How are you going to make sense of direction? Okay.
What do you mean directions?
Oh, so I mean, I started off. Yeah. So from here, from where to where is fine. X and Y is fine. See, but I had said that essentially there was something like a
Concentration in one direction.
Yeah. So there was, so that n was, what to make sense of that z plus z picture, you will really have to take n going to infinity. Yeah. So n comma n is slope 45 degrees. 2n comma 0 is angle 0.
Yes.
How are you going to make sense of any of this on a Cantor set? Say on a Cantor set, how are you going to make sense of this? Yeah. And here, the point is this is some negative curvature features. Really hyperbolic space is negatively curved. This is really the combinatorial or discrete version of negative curvature. This thinness of triangles is a synthetic thing where even if you lose calculus infinitesimally and you can't calculate any curvature, nothing, the large scale features of the geometry is exactly the same as negative. And so groups which are perfectly discrete algebraic objects and manifolds, smooth manifolds and their universal covers where you can do calculus can be put on a unified setting. And you can do stuff with that, and there will be lots of theorems which will be applicable to both. Okay. So here's the thing. What is a particular property of negative curvature, say the hyperbolic plane, or non-positive curvature, the Euclidean plane? You take a point, you take all tangent directions. Yeah. Now you look at geodesics in those various different directions. If you take two directions and you look at the geodesic, they never come back and meet again, right? The distance between two geodesics keeps increasing. Yeah? So now you put a geodesic ray. Yeah? That gives you, say, a point at infinity, right? So here that makes sense. So infinitesimally nothing makes sense. Asymptotically everything makes sense. So you define the boundary is really asymptote classes. Again, there will be little fudge factors. You're allowing triangles to be thin, which will mean that the degenerate triangle, geodesic bigons, yeah? So say A and B, bigons will be, say, you start off at A and end at B. Bigons like this will be uniformly bounded. This distance will be less than equal to delta because it's a degenerate triangle. Yeah? So essentially, again, if you look from far, there is really one geodesic between any 2 points, up to this bounded fudge factor. Okay. So now,
You were going to try to make sense of direction? How did
yeah. I've not yet done it. I'm doing it. So here's the thing. This guy has this boundary. So this boundary, what is the boundary? It is precisely asymptote classes of geodesic rays starting at a point.
Okay.
So asymptote classes means if they remain a bounded distance from each other, you say that they are equivalent. Yeah? And that gives you a point at infinity by this is the exponential map. I mean, the exponential map in non-positive curvature in a manifold setup says that geodesics don't meet. In the sphere they do. So the sphere is very positively curved, these guys are negatively curved. So those rays were giving you point, but that was a unique direction because you were in a manifold. Here you are allowed this finite amount of fudge factor, that's all. So asymptote classes are this boundary. Use this boundary, so what was infinitesimal, what was the tangent space, unit tangent space now has gone off to infinity, use that to parameterize directions. Okay? Now we want
So directions are parameterized by asymptotically large geodesics.
infinite, semi-infinite.
Infinitely large.
But why do you care about directions only and not the points, individual points in the?
Because the individual points part will be used to calculate things, but we'll be changing we'll be allowing the generating set to change, right? So any 2 points which are some finite distance apart, in some other generating set there will be a distance 1 apart.
Can one not talk about its expected distance when you integrate?
No, because the generating set, then you'll have to put an auxiliary measure on the generating set, it will be complete rubbish. I mean, it will not give you anything meaningful. There's no canonical way to choose, that's all.
Quantum gravity.
Huh?
When you are fluctuating.
So we'll come to that. Hopefully we'll come to this pure speculation at the end. Because I mean, there are speculative aspects at the end of this, which will hopefully connect up to that. But
So now you use the boundary to say that from one point you can connect all the points on the boundary by shooting geodesics.
exactly.
And using the boundary, you will say this point is different from this point through some boundary distance, which is some sort of a measure of the angle.
You can do that. So that's absolutely true. So 2 points, the boundary also comes equipped with a metric. And essentially it's what's called the visual metric. I mean, so you have two fellows shooting out, and this point and this point, you put your eye here. What is the angle subtended here is a measure of the angle. Yeah? But now you don't have, I mean, you can't take angle between two just discrete sets, right? So what you do is essentially you look at, I mean, the geodesic between these 2 points actually comes in here. Yeah? Yeah? You look at the perpendicular, or the distance between this set and this guy. Yeah? Just so they call this d naught. Yeah? E power minus alpha d naught for some alpha, which will be related to the Hausdorff dimension of the boundary, is going to give you a measure of the distance between 2
Why
points.
should the measure between the 2 points in the boundary care about the thing inside?
Pardon me?
The distance between the 2 points in the boundary, why does it care about this bulk point there?
Oh, because, which bulk point? This?
No, the one that you are anchoring everything to.
Oh, the metric depends on where you're looking from, right? So for example, just think of the hyperbolic plane. Yeah? If you are here and here, this is going to be this. But if you are here,
No, but you could define
No, these are geodesics.
No, just geodesic than geodesic there.
Yeah, but that's infinite, right?
It's this conformal business, right? There's no
Any
metric
two-
on the boundary of radius. So up to a conformal.
Yeah, but
Say 82 points are
yeah. So it's they are related by a Mobius transformation. So conformally they are the same. But that's a coincidence. Yeah. Here yeah. Okay. All right. Yeah. So this is of course. Okay. But here you do have a conformal structure. Yeah. You don't have exactly a conformal structure. You have a quasi-conformal structure because you are allowing this fudge factor. Yeah? So the group acts also on the boundary. Yeah? So what was happening in the case of the hyperbolic plane, you had the Mobius group acting. So if you had, say, just the z goes to 2z or whatever, then the little neighborhood here is going to get stretched to something, right? The distance, I mean, obviously the distance is changing. Yeah? Conformal structure is remaining the same. That's true. Yeah? So here you're going to get same conformal structure changes. If you take little balls of radius epsilon around that, that's going to go to a set. It's going to get trapped between some epsilon 1 and epsilon 2, where the ratio between epsilon 2 and epsilon 1 is fixed. So basically, infinitesimal, if you think about it, its circles go to ellipses of bounded eccentricity. Okay? So essentially, that's where the fudge factors translate to. Yeah, you don't quite have a conformal thing. In fact, if you allow, even in the ADS situation, if you allow your metric to have variable negative curvature, hyperbolic, I mean negative, then you're not going to have a conformal structure.
This fudge factor, I mean, when you didn't use any fudge, I mean, if you just work on the Cayley graph for some group,
Yeah.
then there is no fudge factor, right?
No, that's true. But the point is, group is acting.
Okay.
Well, group is, I mean, so what, I mean, the geodesics are not going to be unique now. There's going to be some fudge factor between them. Two geodesics landing at the same point are going to be within some delta of each other. Yeah. So which geodesic are you going to move along? So basically here there was some unique guy through which you could scale, and now it's no longer there. Yeah.
I mean, now meaning when you start.
When you do everything in this discrete setup, the group acts on the boundary. Yeah. So for example, here it was the whole Mobius group. You could take SL2Z, for example, if you want a discrete guy, or the symmetry group of the tiling, the triangular tiling. Yeah. That group acts on the circle by conformal transformations, Mobius transformations. Here, how are you going to even make sense of conformal transformations? Yeah. It's only you just have a metric here. You just have balls of radius r on the boundary defined in this e power minus alpha d naught way. So even this alpha is not something really well defined. Yeah. So it's for any alpha in a certain range, you will be able to define this metric. So in that metric, you can define quasi-conformal structures. But you can't quite define conformal structure. So that's the, so when you see this quasi-isometry, isometries are fudged, right? Conformal is fudged to quasi-conformal, that's all. But the constants are going to be bounded, okay? Now, but you want not just an angle, you want a measure, yeah? This is just going to be, I mean, the angle is going to be just between 2 points, but how are you going to measure sizes of balls? If finally you want to say that almost every with respect to direction has some nice behavior. There is a natural measure called the Patterson-Sullivan measure. What do? Now you start off again on the finite group, take a ball of radius n, take the uniform distribution, yeah, and let n tend to infinity. It's sort of the naivest thing that you can do. And you do get nice stuff. You get the weak limit of this actually is supported on boundary G, nothing inside gets any mass. And that limit is called the Patterson-Sullivan measure. Okay? And this measure gels very nicely with this metric. Yeah? Yeah? Basically, this metric, if you take this metric, take a small epsilon ball around it, epsilon to the Hausdorff dimension is absolutely continuous with respect to this measure. Okay? So that Hausdorff dimension, which is what I was saying initially, for the circle, it's 1. Okay. So now there are two, now we'll put there are two different almost everys. There's going to be almost every direction. This is going to be with respect to this Patterson-Sullivan measure. Almost every omega geodesic is going to be, now we go back to our first slide. This is the point at which the two things are being put together. Omega refers to omega is being sampled from this edge set with probability. So there are now two different things. This part is classical. This is for classical meaning where it's deterministic. But now you have a measure on the boundary. Yeah. This is to measure directions. But now you want what if you run percolation on this scope? There's a different measure that comes in, which is this product measure on the edge set. Okay, so now we are starting to put the two together, so you can ask your question.
So when you said you had this uniform measure on all the points,
Yes.
big ball, and then
Yes.
so these are all the places where I could start my geodesic going up to infinity?
No. No, it's what is the measure? See, the boundary fellows,
Yes.
say take a sphere.
Yeah.
There's some Haar measure or Euclidean measure on the sphere, right? It's not just an angle. The angle is just between two rays. How do you measure the area of that guy?
Okay.
That's given by this Patterson-Sullivan measure. That's all. See, if you want.
Every point has equal weight and contributes to the.
Yeah. So basically, it's a version of. You are trying to say that okay, all the points at boundary have the same
count
weight.
The density of points in a
Yeah,
neighborhood,
but that doesn't make sense because the boundary is
so
an
you're doing
uncountable
a
set.
job of that.
So one does a finite version of that and then takes a limit.
Takes a limit, that's the.
That's
I
it.
should just think in terms of itna points on.
On the boundary, yeah. So that's actually a nice way of thinking. Basically, that is the way one does computations. You take a very large ball and just count points.
Count how many on the boundary.
That's it. That's
Go to
it.
infinity as in.
Everything will go to infinity exponentially.
So some.
So no, that's why you take the uniform measure. You just take the uniform measure. So you divide out by the total number of points.
Yeah, and most points are on the boundary anyway.
When you pass to the limit, all points are on the
All
boundary.
that's
Yeah, the interior gets zero mass.
Yes. Okay, so that's the measure.
That's the measure. That's the measure. We'll see. What do we want to do? We want to make a statement about almost every geodesic ray,
Yes.
but with respect to almost every direction. But how are you going to say what does almost every mean? Yeah,
Now by direction you mean.
it's a point on the boundary.
Point on the boundary.
A point on the boundary, but almost every means with respect to
This measure.
this particular measure.
Yes, got it.
Yeah.
Okay.
And now when we refer to almost every omega geodesic, where does omega range? Omega ranges in this little omega, is your sample space. This ranges in this capital omega p.
Ah,
Okay?
got it.
So I'll use almost every in two different senses. That's why I'm
Now
explicating.
when I go back to the discrete case, every edge does discrete setting. Every edge does have some rule that.
That's right. Now the two things are going to be
And
put
you look
together.
at geodesic with respect to that. And
Exactly.
Then look at its
So there's a deterministic geodesic. Now there's an FPP
now the
geodesic.
first slide is connected with.
First slide is now being connected to the two things.
Got it.
So this Patterson-Sullivan measure.
Yeah.
Can you say something about how uniform is it? Does it depend on the graph that you consider?
It changes. It changes.
So
It definitely changes. But there's a quasi-conformal change between one and the other. It's not too much. There's going to be, from each point you can more or less associate another point. Yeah. And there's a canonical homeomorphism, for example, and that homeomorphism is quasi-conformal. Yeah.
So for example, for this point characteristic, every point of the boundary is equally likely.
Yeah. So this is how do you make sense of every point on the boundary equally likely?
Like this.
This is the meaning of every point on the boundary is equally likely.
But there are cases, for example, where it changes the measure with angle.
No.
So what do you mean that you normalize by the uniform measure if the measure to begin with is uniform? That would
I don't understand what.
So
The measure is on. So take a ball of radius. Say take the free group. Yeah. Take a ball of radius n. Essentially, that's out. It's 2 power n on the boundary, and something like 2 power n minus 1 will be the stuff inside.
Correct.
So essentially all the points, only the points on the boundary will pick up the most.
Yeah.
So just put 1 by 2 power n, 1 by 2 power n everywhere.
Correct.
So now you have a set
Stop
with.
only on the boundary.
Just-
What
just-
fraction are on the boundary and where on the boundary?
Yeah. So just put Dirac mass 1 by 2 power n. That's your approximate to this Patterson-Sullivan. Let n tend to infinity. All the mass is now supported in what? In the tree union the Cantor set boundary.
Correct.
As n tends to infinity, all the mass goes and accumulates on the Cantor set. Nothing remains inside. Yeah? That's your Patterson-Sullivan measure.
Got it.
Okay? And so when you may want to say something about directions, you want to make sense of this. This is the measure with respect to which you want to say almost every.
Yes.
Okay. So there'll be these are the two senses. So now I think I'll be able to state at least a few theorems. I won't be able to, in any case, there's a physics talk, so no proofs are required, right? Okay. Okay, I claim that these are my claims now.
Okay.
Well, I think I had it on the first slide, which basically said that all of this is joint work with Riddhi Pratim Basu, who's a probabilist. Yeah. So it's this probabilists typically work on ZD, and hyperbolic geometers know nothing of probability. So this was a way of putting these two things together and sort of essentially doing it in the general setup. Okay. So here's the thing. You say that a path, any path, yeah. Now it's any path. It could wiggle all over the space. Yeah. We really have to deal with this because we want to look at omega geodesics or percolation geodesics have nothing to do, I mean, a priori have nothing to do with geodesics in the deterministic metric. Yeah. You say that it has direction xi if the only accumulation point of this path in the boundary is xi. Okay. So it doesn't wiggle between these. Doesn't do that.
Yeah.
Okay.
Particular kinds of paths.
So essentially, you are allowed to wiggle, but the wiggle becomes smaller and smaller with respect to our this hyperbolic thing. It accumulates on a point. Okay. So that's what you got. That's the meaning of having a path having a direction. Okay. So the first thing is that almost surely. So basically, here's the thing. Take any point in the boundary G. This is now going to be percolation geodesic rays in that direction mean what? You take a sequence of points converging to it. Yeah. Take for almost, this is where you're putting the two things together. Almost every omega in the sample space. Yeah. Look at sequence of omega geodesics, O, X, and omega. These converge up to a ray having direction sign. So which means basically it says that for almost every point in your sample space and any direction in the boundary, the percolation geodesics, I mean, if you take a sequence of points converging and you look at percolation geodesics, they'll have a unique direction and that will be the direction.
What does ray mean, please?
Oh, ray means just, it starts at one point and then goes off infinitely. If it goes in both directions, it's by infinite, but in one direction, it's semi-infinite. Semi-infinite is a ray.
So it's kind of like the definition of that.
Converges to a ray.
Because you are going closer and closer to the boundary
Yeah.
and you are taking this point.
Yeah, so what you're doing is so there are two things
In
here.
what sense can it fail?
Yeah, so let's see. So here's the thing, okay? So this is your geodesic ray, okay? This is the deterministic geodesic ray.
Yeah.
What you're doing is, you're taking a collection xn
That goes towards
that converges to this point.
Yeah.
Yeah. Now you draw percolation geodesics, it could do this. It could go on.
Because of the different lengths for each segment, it could do all sorts of
It could be,
Is it near the boundary they're all the same? That's what you're saying?
it just goes to a sequence of points which could go.
Near the boundary are basically
Yeah, but the percolation geodesics need not even behave like this asymptotic thing.
not even near the boundary.
You don't know a priori. They are just
But your
paths.
theorem is that they do near the
Yeah.
boundary. Now,
Yeah.
Okay.
Yeah. So this controls the geometry of these percolation.
But somehow the distribution, look, the distribution of length has to have some condition.
Ah, yes.
Otherwise, I could do.
This is very, very soft. This is very soft. Very soft conditions on the row.
Okay. On row.
Yeah, on row. On the passage time distribution. Certainly, okay, here's the thing. Well, always assume that rho is sub-Gaussian, let us say.
Then it's.
Let's say sub-Gaussian, okay? So,
This path just ends at xi, or it also, like the path converges to the ray?
Xn is going to.
Is that sequence
Yeah.
xn?
yeah.
Our final few elements of that sequence?
Yeah,
is
you
the same
can
for
do,
every-
yeah, it's only the last point needs to go to this point here.
Correct.
That's all. You don't care about, it's just a sequence of points, and now you're looking, see, you're taking a sequence of points, right? This is your sequence.
You're trying to go from 0 to xn. Xn is tending to psi on the
That's it.
boundary. And then you are asking what the.
What happens to so you're going to get for each omega, you're going to get a collection of omega geodesics, right?
In some sense, I'm asking is not is the derivative also the same?
There is no
In the
derivative.
sense, I'm saying that our last few elements of the
Along
all
the
the paths.
Hopefully,
along
if you give me another 5 minutes, hopefully I'll make a precise statement to that effect. It's actually, situation is much better than that. It's not just derivative. There's going to be something more, much better.
So this percolation geodesic never passes arbitrarily close
the point is, okay, so so basically what we are trying to do is, we are trying to say what is the geometry of percolation geodesics parameterized by your probability measure space omega p.
So you're saying if it's a Gaussian, is it basically going to become the geometric geodesic if xn goes to
Sort of.
in the end?
It's qualitative, not quite, not really, but
Like that.
close enough.
That will be your next. So you'll say something.
I'll say something about it.
See, it seems to me that your lengths are basically fluctuations of the geometry in the bulk.
Yeah,
Yes.
little bit.
And you're saying that your rule does not allow geometry at infinity to fluctuate effectively. Right?
That's right.
Infinity first.
Yeah.
That's right.
Yeah.
That's right. That's correct. That's correct.
Normalize it. Normalize it.
Yeah. Well,
Yes.
so here's the thing. So okay,
have a very
okay.
broad
Shiraz, let
Yes,
me put a caveat to that.
Yes.
Hopefully, hopefully, are you going for lunch after this?
Yes.
So I'll speculate at least on this, because I don't think the boundary is really held fixed. There's a second order variation there.
Okay, I'd love to hear this.
Yeah. So that's something that that's supposed to be some stuff we want to do with Riddhi just after this. There's a way of measuring all this conformal change, etc. So we'll come to that. What's the second theorem? So this is just the direction of percolation geodesics. Yeah. The second statement says, oh boy, what happened? Velocity exists. Okay. So velocity, recall what we had? So expected passage time.
Yes.
Yeah.
Yes.
Between 2 points, and then for xi belonging to this, define the velocity. Now we've established that direction exists, so we can now ask quantitative things. Yeah. So what is velocity? Velocity is the expected time of passage from O to xn divided by the deterministic guy. So it's time by distance rather than distance by time, but okay, fine. Yeah. So it should be.
By the deterministic time with all lengths equal 1.
Yeah.
Right.
I mean that's how you calculate, right? In when water flows, is how fast does it reach when the distance in the deterministic thing is. Right?
Expected time divided by the time in
Okay, yeah, that's right. So, but this is Wick rotated, so everything is
Euclidean.
everything. Yeah.
So this is the Gaussian you're talking about.
What is the Gaussian? Ah, yes. Okay. Oh, so that means actually the previous fellow did not require that assumption. Okay, I put this assumption here means yeah. So I mean, I always think of it as put this thing as safe but.
That's required only here.
Okay, so provided the limit exists, this is our velocity. Assumption is now that rho does not have any atom at 0 and it's sub-Gaussian. So, meaning that there is not a concentrated fixed Dirac mass of say total mass say 20,
Like some lengths
1
are not
2 by
zero.
10.
Like some finite fraction of length.
Doesn't collapse.
Yeah.
The finite fraction of lengths are not 0 and it decays at infinity fast.
Yeah. So the function rho is not, I mean, it's a measure, right? So it could have, parts of it could be concentrated at finitely many points, the rest could be an integral. You don't want that. You have a continuous distribution. At 0, you want a continuous. Yeah. 0, it's, I mean, the mass of the point 0 is 0. Okay. That's it.
You don't want too many short circuits.
Yeah.
No, but
Actually,
the measure could have support at 0 or just
Support is okay. He doesn't
support.
want it down.
Yeah, you don't want a Dirac there. Yeah.
So he doesn't want finite fraction.
Mu of, if rho of the singleton 0 is 0.
Yeah, no short circuits.
He is constant and by some choice of scale in the
Okay, hey, you're not supposed to read the Okay, so here's the statement. The velocity actually exists. Yeah, so a priori there's no reason why, I mean, so in fact, it's only exists, yeah. So velocity in for almost every, now this almost every is with respect to?
velocity depends on O.
No, it does not. It does not. It does not depend on the origin. It just depends on the direction. So this is a statement that you define it for O, but it's independent of O. Why? Because it's going to be just some finite distance apart. You're going to take something infinite, all that's going to go to 0 because you're going to divide out by some larger and larger number. So for almost every, but this is a fact, that is almost every, the velocity in this guide direction exists. Further, it's actually constant. So almost every direction is really uniform. This is the real reason why I was stressing all this 2n choose n at the beginning. This is something, there are two features of difference from the Euclidean case. First, you don't get every direction. In the Euclidean case, you get every direction with not too much difficulty. The velocities change because of this larger number of paths. Here, velocity remains constant. And this almost every is not a feature of the proof, it's a fact. So even with the free group, Here's an example where you can change velocities in different directions. The existence of velocity is not true, yeah, in every direction. So take the free group, yeah. But now take the Cayley graph where A remains the same. One of the generators remains fixed. The other, you change the generating set to B, comma B square. So basically plus minus 1, plus minus 2 in one direction, 1 in one direction, yeah. So this is that stuff. I mean, in the plus minus 1, plus minus 2, there are more than one geodesic to the same point, right? You have n plus 1, 2, 0, comma n.
Yeah.
In the other direction, so it's going to be faster there. In the other direction, it's slower. So that means now you have the A to the infinity direction and the B to the infinity direction. The velocities are different. Yeah. Now, if velocities are different in two different directions, you can cook up a word, and which will give you a direction in the free group boundary in the Cantor set, where the velocity will just not exist. What is that word? Take A power 10, then A power 10, B power 10 power 10. Then A power 10 power 10 power 10. Then B power 10 power 10 power 10 power 10. Which means that the last term kills everything else. So that means the velocity will be in the A direction, velocity will pick up, then it will jump to the B direction velocity, then it will jump. So basically there will be directions where velocity will just not exist. Okay, so this is not this is a feature of hyperbolicity. We don't know what is the class of groups, basically the class of graphs, for which velocity is actually, it should really impose strict symmetry conditions. For example, if A and B are symmetric, then velocities actually exist in every direction. So the point is that if it does exist in every direction and it's continuous, then it will be a constant. Yeah. So what does, it will be globally a constant.
And by rescaling your rho, you can set that constant to 1.
Rho?
By recentering your velocity your distribution of rho. That the constant is not 1 is basically because the lengths are not peaked around 1. Right?
Yeah, why should it not be?
No. Rho is your passage time distribution, right?
Exactly. So suppose your passage time was peaked around 1.
Yeah.
Then this constant would be basically.
Oh. No, it doesn't quite work that way. No, it doesn't quite work that way.
It depends on the width as well.
Yeah. Oh well, let's see. Oh, okay. Yeah, okay. So I never bothered about that because we always wanted to think of things up to fudge factors. It's actually no, that's not true. So the point is you really have to work a little bit to prove that this is non-zero. Yeah, you don't know that it's non-zero A prime. It is true.
So it depends on the width. Okay.
Yeah, it does depend on the width. You want a lower bounding this away from zero because it's a tiny bit of work, but you do require it. Okay.
Right.
So here's the statement that you cannot upgrade this.
To all points.
Yeah. Okay. So this is your question about what happens at infinity. And then what happens is coalescence. So if you take two semi-infinite paths, they are said to coalesce. If beyond some x naught, they just coalesce. Okay, they come together and then follow the same path.
Could I make a small comment? It
Yeah.
sounds to me like you're saying that there is these fluctuations from my language.
Yeah.
Fluctuations renormalize the area as radius.
I'll have to parse that.
Yeah.
So let me finish this. I'm just 2 minutes away, even with the 15 minutes latitude. Okay. So coalesce, so here's the theorem that for almost every omega again in this, any 2 points O1 and O2 and any direction xi, omega geodesic rays O1 xi and O2 xi almost surely coalesce. So basically this is the version of having a derivative. Beyond that it does not have to follow the word geodesic, but it will have to follow the same path. Okay. And this is really again, it's basically because word in the determinist geodesics, at least if you remember this graph that was drawn there was this path, this was a geodesic ray and the straight guy was also a geodesic ray. There were two geodesic rays heading in the same direction, but they were remaining a fixed distance one apart. That can't happen here. So the deterministic setup and this, they're qualitatively there's some
So if
difference.
you start at two different things, if they're going to that direction, finally
Yeah.
they go together.
Finally they go together.
At points near the boundary are determined just by where they hit the boundary, right?
Pardon me?
Yeah.
The paths near the boundary are determined only by where they hit the boundary. They
That's
forget
right.
about
Yeah,
where they came from.
That's right.
Eventually they all become.
That's right. Yeah. But we haven't yet explored quantitative versions of this. Okay. If you start 2 points how fast will they coalesce? So our proof does not quite give you that. It will have to be sort of worked out. Okay.
Free areas. It's more than that.
Huh?
Because of
All the features
fluctuations
you said so far
Strong enough.
are kind of simple to prove for this concurrence with the
No.
uniform method.
No, it was not known. For the Poincare disk also it was not known. Nothing was. Only case that was known is the tree where all omega geodesics are the word geodesics. So even for the tiling, I mean there is nothing for the Poincare disk. You have a tiling for the Poincare disk. So Fuchsian groups. Yeah. So this reflection group has the dual lattice. There's a dual graph. For that it was not known. I mean, so it's okay. So now what about the distance?
Something is confusing me. I thought in hyperbolic spaces.
Yeah, okay, good. Now I've gotten as far as I wanted to, but I want to say what is there in this slide, and I'll come back. Can I come back to you?
Yeah, sure, please.
Yeah. So so this passage time, it's a random variable. Yeah. What about its variance? Yeah. So the velocity was giving you the mean. Yeah. What about the variance? That also grows linearly. Okay, with time. So essentially there exists C1 and C2. We haven't gotten the exact thing. So that it's actually in terms of distance, variance grows linearly. This is again something that's very different from Euclidean. In Euclidean, this is sort of a big open problem. It's expected to have some universality class, which you guys probably know much better. It's
so it goes linearly with what, please?
With the word distance. Oh, n. So you take xn is a sequence of points which go off to infinity.
And n is along generators.
Xn is distance of xn from 1 is n.
I see.
Yeah.
So this is like
I see.
So variance
Number of edges
becomes
taken.
infinity as you go to boundary.
Yeah. No, that you
That has
expect.
to happen.
That has to happen.
It's how it
Yeah, how you normalize it is unless you normalize it won't happen.
The length
Because
itself
it's-
is infinity. So the variance is the same order as the length, you're saying.
The variance is of the same order of the length.
That's
This is
quite surprising, right? I guess.
well the geometry of the space. I have not said anything about the geometry of this.
In this,
So if you take here's a way of thinking. If you take a free group, there is only one ray going off to infinity in any direction, right?
correct.
So what is it? That you have i.i.d. Variables n of them.
So
So of course it's going to be
Yes.
linear.
Yes.
Yeah.
Yes.
But there it's a very deterministic setup.
Correct.
The geometry of hyperbolic space dictates that the qualitative behavior is still like
Still like that.
the tree case.
It's still like that. But like if I take n to the power n, it will not.
No, in fact, it's not expected. I think there are some very weak bounds. I don't know much Euclidean percolation. Yeah, it's d power, I think, in dimension 2, I think the expected thing is either 2/3 or half or something like that. Am I being recorded? I don't know. Okay. So, yeah.
In that sense, yeah.
Yeah. Okay. And so this was conjectured. This was conjectured. In the hyperbolic group case, the variance was conjectured. So there's a mean and there's a variance. One expects a central limit theorem to hold. Okay. But we don't know that. Okay. Yeah, you had a question.
So I thought that neighboring geodesics in a hyperbolic space
Yes.
would veer off from each other.
Ah, so
now basically we are normalizing this.
no, not okay. So what's happening is okay.
What is coalescence then?
Okay. So what happens is that
Run
you take
coalescence backwards, it's veering off.
run coalescence backwards as well. Yeah. So you have 2 points.
Yeah.
And so what happens in hyperbolic space is that if you have 2 geodesics, they come and they will stay close for some amount of time, and then they'll exponentially diverge away again. That's the qualitative behavior of geodesics. But if you carefully direct your 2 things to be asymptotic at infinity, you could do that. So for example, here is what are examples of things which are asymptotic?
You start from the boundary and go inside.
No. So you have 2 points, yeah? You have 2 points on the upper half plane, let's say. Yeah? These guys are directed towards the same thing. So if they are just going off to infinity, they are both geodesics directed to infinity. Then what is this distance? This distance is going to be d by, I mean, if the Euclidean distance is e, then dis divided by, if this is 1, this is, well, essentially it's, if this is 0, x is 0, comma, d, c, it's going to be c, right? So the distance, I mean, they're becoming asymptotic, right? It's the distance, I mean, if you have 2 geodesics heading towards the same point, they become asymptotic, become tangential. The hyperbolic distance goes to 0. On the other hand, exactly. On the other hand, if you have something heading towards some other point, say here, then you have, this is the semicircle is your geodesic. Say this guy, okay, so it's this is some other vertical guy. There is some part where there is a mutual perpendicular, This is the part where they'll be closest. Below that, they'll be exponentially diverging. After that, they'll be exponentially diverging.
Sorry, could I ask, is there
Yeah.
a relationship between this constant and the constant that appeared in the velocity?
I have no idea about the constants. So it's just
Constant C1, C2 and the mean of V.
Yeah, exactly.
no. I mean, at least our proofs won't give it. I mean, these are not effective so far. C1, C2 is just it's a crude lower bound we get.
Why? Because, the fact that there is a variance at the same order as the length is sort of surprising. Right? Things not really behaving like ADS spaces at the moment. But the velocity was also not 1, which also meant that it was not behaving like ADS space. I was just wondering whether they were both behaving like the same scale ADS space. And that this variance is just the variance in that scale.
How many scales will be in the probability distribution that I,
What? How many?
in your probability distributions you might have some scales.
Yeah.
Probability distribution, what scales mean?
It's just one.
It's e power ax squared, then rho of x dx. So there is some constant a greater than 0, such that happens.
But I'd like to get the square root 2's right as well. I mean, there should be a precise relation. If it's really like, it's just behaving like ADS is not doing anything at infinity.
No. That we certainly do not expect. That we certainly do not expect. What happens is that these percolation geodesics, which means that everything coalesces, means at infinity, if you look at these percolation geodesics, for each little omega, it's going to give you a tree structure. That tree structure is going to give you a Busemann function, a horosphere, I mean the collection of fellows which are quote unquote equidistant from infinity. Yeah? So this in the hyperbolic plane will be this horizontal guy. This is the fellow which is sort of at equidistance from infinity. This guy actually is, so if you take a group element acting on that, that's going to scale by something. That it's going to go to another horizontal. The distance between these two horizontals reflects in the conformal change at boundary. I mean the scale, yeah. How large that radius becomes. That part I don't think is going to, so there is going to be, first order I think that's going to be the same, second order I think there is going to be a difference. So what you're getting is really a random conformal map, quasi-conformal map at infinity.
Because the measure is this i.i.d. that you're picking, right?
That's right.
And there is the boundary condition is kind of Neumann type boundary condition.
It's at infinity, no? It's at infinity.
Those things also fluctuate quite a bit, right?
Which ones?
The edges, the lengths of the edges very close to boundary also fluctuate.
Absolutely, all edges are allowed to fluctuate. All edges are allowed to fluctuate. It's just, so yeah, that's right. So which means that there will be some transverse direction oscillation of this conformal. That should be a second order wave. It's spinned, yeah, but it's spinned only up to first order.
Meant by radius of ADS is measure of curvature in the continuum case.
Pardon me?
Measure of local curvature of the
Yes,
continuum
yes.
case. He was talking about the renormal.
Yeah, so now we'll have to,
We can do that.
yeah, we can do it. Okay, shall we stop or?